order to multiply?
Like pairs.
Well, what do you mean by that? Like pairs?
Something that's both equations have to have the same radical.
Close. Same. Closer.
Root.
Same root.
That's what I meant by
Yeah, I know. The thing is, the word radical, the word root, the word radicand, like they're all different things. We'll talk about that a little bit more today. To multiply, you need the same root. So for example, you're looking at a bunch of different numbers in your cards. What are the roots that we see? I see a third root, right? Cube root. What else do I see? Square root. So if you wanted to pair some up, they would just need to be the same root. So there's a lot of different combinations. You just need to pick two that are square root, or two that are a third root, or maybe you got extra, ambitious and chose three, because you could have gone boom, boom, boom. All three square roots, all three can be combined, right? So can somebody give me an example of two that they tried, that they did? Yeah, go ahead, Leo.
5 times the third root of 2 times 5 to the third root of 5.
5 times the third root of 2 times 5 times the third root of 5. Okay, I think that's going to work. Now, when we're multiplying these, we treat the numbers on the outside separate than the stuff going on in the inside. And in fact, sometimes, if you want, it might be easy for you to just think of this as, well, it's this times this times this times this, right? It's all multiplying by everything. So I can rewrite this to be 5 times 5 times third root of 2 times third root of 5, right? And now I can be like, okay, these things go together, these things go together. So this is 25, and then the third root of 10. And I can't do anything with the third root of 10 that doesn't break down or anything, right? Because there's no group of 3 in there. All right, somebody want to give me another one they did? Anybody? Yeah, go ahead.
the square root of 12 times 5 the square root of 5.
Okay, cool. All right, so then if we're thinking about multiplying the numbers out front, well, what if we don't have a number out front?
Then it's just multiplied by 1.
Yeah, it's just like having an imaginary 1 out there, right? So 1 times 5 is 5. And then I have the square root of 12 times 5, right? That's what happens underneath. And that would be 5 square root of what? 60, right? And then I would ask myself, well, maybe 60 breaks down, right? Maybe 60 breaks down. So this is where we go into that other skill where we say, okay, square root of 60, can I break that apart? Now, there's a couple ways to do this. You can say, well, maybe there's a perfect square inside of 60, which there is. What is it? 4. So this would be the square root of 4 times the square root of 15, which would be 2 square root of 15, right? Which would then be 5 times 2 times square root of 15, which is 10 square root of 15. Now, the other way you could have found this 2 square root of 15 is if you just started breaking this thing down all the way. 60 divided by 2 is 30, divided by 2 is 15, divided by 3 is 5, and I've broken this down as much as I can. These are my pieces that I found. Square root of 2 times 3 times 5, and I look for pairs because a group of 2 is what I would need for a second root, right? So this group of 2, well, 1 would come out, 1 would go away, and I'd have 2 square root of 15. Same thing, 2 square root of 15, right? Plug that back in, and then we end up with 10 square root of 15. Okay? So those are all the skills that we talked about with multiplying with the product, okay? Okay, so for your lesson, your second warm-up was about combining like terms, right? Like many warm-ups, I give you a piece, you definitely should be able to do, and then a piece that I'm hoping you can kind of connect the dots to do, but I haven't taught you. Okay? The first part we should be able to do, right? We're just combining like terms. But we like to review why it works, because then we can use that for a more advanced situation, right? So what are the things I'm looking for when I'm combining like terms? Two things.
Same variable, same exponent.
Exactly. Same variable. Same exponent. Now, these are all x, right? So we aren't really even worried about the variable here. We're just worried about do they have the same exponent, right? If there was a y in there, well, that couldn't be combined even if it had the same exponent, right? Okay, so there's a bunch of different methods for this. I like to use the underlying method. Some people just kind of do it in their head, right? Just be careful with your signs. This is an x to the fourth, so I look for any other x to the fourth, and I underline it like so. No, no. And then once I find all my x to the fourths, I start over. And my next thing gets 2 lines. X to the 1, okay. No, yes, this is x to the 1, right? And then the only thing left is x squared, so that gets 3. Make sense? So you start with your highest one. I have 2x to the fourths, and I add 7x to the fourths. How many x to the fourths do I have? I have 2, I add 7, I have 9. And there's a reason I'm phrasing it that way. I have x to the fourths, I'm adding x to the fourths. Think of them as units that are being added to each other. They are terms, they are like terms. I have minus 5x squared by itself, and then I have minus 3x and 6x, positive 6x. So I have 6 x's, and I take away 3 of those x's. I have 3 x's left, right? So there you go. This is combined. Okay, so now it's basically the same thing, but you have to look for your like terms now. Okay, so we'll talk about the rules, but I'll show you this in a couple different ways. The first way is this. This is confusing for people, but I bet you I could turn this into something that would be probably easy, right? Just by replacing all these radicals. So let's say x equals the square root of 2, y equals the third root of 5, and z equals the square root of 3. Okay? So I'm just going to set variables for each of the different ones, right? Well, if I replace based on that, well, instead of 5 square root of 2, I'd have 5x plus, instead of 7 third root of 5, I'd have 7y minus 8 square root of 2. So what was square root of 2? X plus what square root of 3? Z minus y. Now, if I gave you that problem in blue and said combine like terms, I think everybody here would find it pretty easy, right? Be like, oh, sweet. 5x minus 8x, 7y minus y, and a z, right? It's the same thing. You just have to recognize what like terms are in this situation. The like terms here are this one and this one, this one and this one, and then this one's by itself. What made them like terms then? What needs to be the same this time?
The root and the number that's underneath it.
Exactly, yeah, the root and the radicand. So same root and same, and I'll say base because I haven't defined radicand yet. I'll do that below. Same base. Think of it as a base or a radicand. We'll talk about radicand a little bit more in a second. Okay, so if I'm doing that, again, I want to think of it in terms of units. I have 5 square root of 2's. I take away 8 square root of 2's. How many square root of 2's do I have? Minus 3 square root of 2's. Right? And it's a little silly to talk about it that way, but it helps you remember what you're doing, right? I have 7 third root of 5's. I take away 1 third root of 5. How many third root of 5's do I have left? 6, right? And then square root of 3 all by itself. Okay? So, one more thing to add in both of these situations, right? What did I do to combine the like terms? Like I had 2x to the fourth, 7x to the fourth, I ended up with 9x to the fourth. What's the operation that occurs? Addition or subtraction of what? What's that called? The coefficient, right. So in both cases, just add or subtract coefficients. So first you identify your like terms, and then you add or subtract your coefficients. Okay, so let's just kind of summarize real quick. If we're adding and subtracting radicals, we are combining like terms. And just like with non-radicals, we're looking for two things. We want the same what? What did we, first thing we said had to be the same up there? The root. And then also the same radicand. Or in other words, base. If it was an exponential form, we'd call it a base, right? So let's review that real quick. If you have a root, like the nth root of a, right? There's three pieces that we kind of want to know vocabulary-wise, right? This n right here is your root. This symbol, this root symbol, where like a square root, cube root, the little slash thingy, that's called your radical. So I'll say, oh, it's under the radical, and then that's our radicand. Okay? Okay. So, go ahead and check out what these are and tell me, or tell yourselves, are they like terms or are they not? So yes or no. And then, if you can, say why and then combine them if you can. Okay? All right. So, third root of 5 and third root of 6, are they like terms? Could I bring these together? I hear both. What are the two things we need? Same root. Okay, that's good. Same radicand. That's not the same, right? 5 and 6 are different, so these are not like terms. Okay? How about over here? No.
Not the same root.
Same radicand, but not the same root. I got 2 and a 3, right? What about here?
Yes.
Yes, very good. Everything works out fine. I got boom, 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 boom. Okay, so if I brought these together, how much would I have? How many fifth roots of 9 would I have? 8 fifth roots of 9. Right? How about this one?
Yes.
Ooh, why? How?
Because if you change the exponent to radicals, it's the exact same thing.
It's the square root of 7, right? So I'd have how many square roots of 7s if I brought these together? 4. Good. All right, if you haven't yet, work on these two top or actually 3 wait, no. Yeah, 3 problems. 3 problems. So now you're just practicing, right? Bring together what you can. All right, so I'm going to go over these 3, and then the third one will kind of give you a hint on how to do the rest. The third one has a hidden like term in it. All right, very basic one, right? If I have 1 fourth root of 10 and I add 7 fourth root of 10s, how many fourth roots of 10s do I have? 8, right? 8 fourth root 10. Okay? Here, you can change the form of these. So this is 2 times the fifth root of 8 minus 10 times the fifth root of 8. So I have 2, I subtract 10, I have minus 8 fifth roots of 8. And now this one. Well, 3 to the 1/2 I would rewrite as what? Square root of 3, right? Plus 5 square root of 3 minus 2 square root of 75 plus 3 square root of 15. Okay, what can be combined here? Which is how many? 6 square root of 3 minus 2 square root of 75 plus 3 square root of 15. So are we done? Is that as far as we can go?
No, because you could extra, we can multiply more into the exponent. To get 75.
Oh, you went up. How? No, yeah, I would break down. So you were saying something about this one. I would break 75 down. So if you simplify, if you simply simplify 2 square root of 75, it would be 2 square root of 25 times square root of 3, right? Square root of 25 is 5. So it would be 2 times 5 times square root of 3, or 10 square root of 3. So 2 square root of 75 is actually 10 square root of 3. So I get 6 square root of 3 minus 10 square root of 3 plus 3 square root of 15. 6 minus 10 is negative 4 square root of 3 plus 3 square root of 15. Can I break down the square root of 15? No, because it would just be 5 and 3, right? Both still under a square root. So this is actually as simple as this one can get, and therefore it can't be simplified and combined. Okay? So that's what you need to practice with these, is if you simplify, can you then combine, right? So simplify, then combine.
My brain's done. You have to multiply.
You tried to bump it up instead of breaking it down. Okay. Well, you were close. Okay, so work on those, and I'll hand out your homework. So here's the thing about these, is there's actually a little bit of a clue here, because I'm trying to break the bigger one down to the other one, right? So what I really want is to turn the third root of 54 into the third root of 2. So that means I can kind of divide by 2 and see what I get, right? Because I'm trying to get to 2. And if I divide by 2, I get 27, which is what I was hoping for. Now I have that perfect cube that I can turn into 3 third root of 2, right? So this is 3 third root of 2 minus third root of 2, or 2 third root of 2, okay? Here, what do we think? Well, when in doubt, just simplify and see what you get, right? This would become square root of 4 times square root of 3. That's 2 square root of 3 plus 5 square root of 6. Can I do that? No, they're both fully simplified and they're not the same radicand. Okay? This one, well, now that I changed the typo, you have the third root of 5 times the third root of 40. Well, again, you kind of have a little bit of a clue here. You're trying to get to the third root of 5, so you would change this one to the third root of what times the third root of 5? 8, right? Which means I have the third root of 5 plus 2 third root of 5, or how many third roots of 5? 3. And then this one, well, can I simplify either of these at all? No. So there's nothing you can do. It is what it is. All right. Go ahead and work on your homework. Ask questions if you need to. You got 5 minutes, so plenty of opportunity to get some done. Front side was all about multiplying, pulling apart, or bringing together, right? And then simplifying either by finding perfect squares or perfect cubes or perfect whatevers, or jailbreak, break it all the way down, look for groups that are the same as the root number. So anything on the front that we would like to see? 2, 4. Okay. 5. Say again. 10. 2, 4, 5, 10. Actually, I'm going to do the answer key. Make it easier. 2, 4, 5, 10. Okay. So number 2. Okay, so again, a couple ways you could do this. You could say, well, I know the square root of 294. I could maybe try to find perfect squares inside of that. So I take 294 and I divide it by, I don't know, 16. It doesn't go in evenly. And then I divided it by 25, and it doesn't go in evenly. I keep trying a bunch of them, and then I find out that actually it's 49 times 6. 49 times 6, right? So, okay, that means this would be 7 square root of 6, right? Which is what it simplified to. Now, maybe you don't want to just try to find perfect squares. Maybe that seems like it would take too long to just guess perfect squares. Well, in that case, you would break down 294. And you'd ask yourself, well, what goes into 294? We can start with 2. So if I do 294 divided by 2, what do I get? 147. Okay, 2's not breaking down anymore. What goes into 147? Well, what's at the end of it?
7.
So let's try 7. Maybe that goes into it. I don't know. Grab your calculator. 147 divided by 7. It does work, right? So look for clues, okay? And then 21 would be 7 and 3. Okay, so I got 2, 7, 7, 3, right? This becomes square root of 2 times 3 times 7 times 7. Okay, I look for that pair. I found it. 1 comes out, 1 goes away. I end up with 7 square root of 6. Okay, so look for those clues. Like if it's 147, that's a weird number. It's not going to divide by 2. Try 7. It's an odd number. Try 3. Like you're going to have to try a couple things. Okay. All right, next one. Number 4. All right, so 243, and we're looking for the 4th root, right? So 243, well, it's not even, so it's not going to divide by 2. Maybe it'll divide by 3. And what do you get when you divide by 3? 81. Now, you can keep breaking this down, but aren't we looking for a 4th root? And isn't 81 4th rootable? So I kind of just stumbled into the answer here, right? It turns out that this is the 4th root of 3 times the 4th root of 81, and the 4th root of 81 is 3. So it's 3 4th root of 3, right? Now you could also have continued to break this down and been like 3, 27, 3, 9, 3, 3. And then you get 1, 2, 3, 4 of them, 5 of them. 1 would come out, 3 go away, 1 stays. Right? So you could have continued to jailbreak it, but if you find a perfect piece that you're looking for, just stop there and take the 4th root. Does that make sense? Okay. If I broke it down all the way, it would be the 4th root of, let's see, just 3 times 3 times 3 times 3 times 3. That's what 243 is, okay? And I look for a group of 4. Within that group of 4, 1 comes out, the other 3 go away, and something remains, so I end up with 3 4th root of 3.
Yeah, that's the jailbreak version.
Yep, that's the jailbreak version. Okay. Number 5. Number 5, you could not simplify any further than it is. It is fully simplified. How can you find that out? Well, you know you need the third root, right? So you're going to start breaking this down. And you divide by 2, and you get 63. And then you divide that by 3, and you get 21, 3, 7. And that's as far as I can go. And the third, minus 6, the third root of 2 times 3 times 3 times 7. Well, I'm looking for a group of what? 3, and there's no group of 3 in there, right? So this can't be broken down. This has to be fully simplified. Okay? Number 10. All right, for number 10, well, again, just like in our warm-up, you multiply the numbers out front, bless you, multiply the numbers out front, multiply the numbers underneath. So that gives me negative 2 times 1 on the outside, and then the 6th root of 20. Okay, well, I kind of already know that I'm not going to be able to take the 6th root of 20, but I'll prove it, right? Because if I break down 20 and I don't find a group of 6, then I can't break it down, right? So 20, well, that's 2 and 10, 2 and 5, and that's it. So minus 2 times the 6th root of 2 times 2 times 5. And I'm looking for a group of 6. I did not find one, right? The best I got was 2. So this is fully simplified at this point, and you're done. So that's how you find that out. Okay? On the back, what problems on the back would we like to see? 16. 13. Anything else? 11. 15 and 16 are pretty similar, so we'll go over 16, that'll probably clear that up. All right, so here, well, I have the square root of 144 over 4. We learned that you can pull that apart, right? So that's the square root of 144 divided by the square root of 4, both of which you can do. Square root of 144 is 12. Square root of 4 is 2, which is 12 over 2, which is 6. Also, 144 divided by 4 is what? 36. So you could have actually just done the math on the inside. But I wanted you to practice this, because this was the skill, right? You're not always going to be able to just do the math. Some of these are, you have multiple options. Okay, number 13. Okay, so you have 3 times and then third root of 27/8. Similar, except you have that 3 out front. So really you have 3 times and then the third root of 27 divided by the third root of 8. You pull that apart because you can do both of those, right? And you end up with 3 times, and then you'd have 3 over 2. Now, how do you multiply a whole number by a fraction? Put a 1 under it and multiply across, which gives you 3 times 3, which is 9 over 2, and that was your answer. Okay? All right, and now 19. Okay, so this one, 16 I meant. 19. Like, I didn't get it, 19. All right, so this one. All right, so the way I would recommend doing these is if you have a number in front, but on the top, but not the bottom, you kind of pull it apart, and you say 5 times the third root of 108, and then you put a 1 underneath it or above it, right? And you go 1 times the third root of 4. All right, just changing the structure a little bit so I can see, oh, wait, I can pull this apart. Because 5 over 1 is what? 5. So really, this is 5 times, kind of like the backwards version of the last problem. 5 times, and then if I have this, well, I can't do that, but if I bring them together, and I say the third root of 108 divided by 4, that's 27. So I have 5 times the third root of 27. Third root of 27 is 3. So I have 5 times 3, which is 15. Okay? Very similarly for number 15, you would bring the 15 and the 3 together, and it would give you the third root of 5, which you can't do, so it would just stay 5, third root of 5. Okay? All right, ready for the lesson?